Poynting vector. In physics, the Poynting vector represents the directional energy flux, the energy transfer per unit area per unit time of an electromagnetic field. The C unit of the Poynting vector is the watt per square meter W/m2. Is named after its discoverer John Henry Poynting, who first derived it in 1884. Oliver Heaviside also discovered it independently in the more general form that recognizes the freedom of adding the curl of an arbitrary vector field to the definition. The Poynting vector is used throughout electromagnetics in conjunction with Poynting's theorem, the continuity equation expressing conservation of electromagnetic energy, to calculate the power flow in electric and magnetic fields. Definition. In Poynting's original paper, and in many textbooks, the Poynting vector is defined as S equals E x h display style math S equals math E times math h where bold letters represent vectors, and E is the electric field vector. H is the magnetic field's auxiliary field vector. This expression is often called the Abraham form. The Poynting vector is usually denoted by S or N. In the microscopic version of Maxwell's equations, this definition must be replaced by a definition in terms of the electric field E and the magnetic field B described later in the article. It is also possible to combine the electric displacement field D with the magnetic field B to get the Minkowski form of the Poynting vector, or use D and H to construct yet another version. The choice has been controversial. Pfeiffer et al. Summarize and to a certain extent resolve the century-long dispute between proponents of the Abraham and Minkowski forms. See Abraham-Minkowski controversy. The Poynting vector represents the particular case of an energy flux vector for electromagnetic energy. However, any type of energy has its direction of movement in space, as well as its density, so energy flux vectors can be defined for other types of energy as well, e.g., for mechanical energy. The Yumov-Poynting vector discovered by Nikolai Yumov in 1874 describes energy flux in liquid and elastic media in a completely generalized view. Interpretation. The Poynting vector appears in Poynting's theorem. See that article for the derivation and energy conservation law. U T equals S J F E display style frac partial U partial T equals math nabla C dot math S math J mathem F C dot math E, where Jf is the current density of free charges and U is the electromagnetic energy density for linear, non-dispersive materials, given by U equals 1, 2, E, D, plus B, H, display style U equals frac 1, 2 left math E C dot math D plus math B C dot math H right where E is the electric field, D is the electric displacement field, B is the magnetic field, H is the magnetic auxiliary field. The first term in the right-hand side represents the electromagnetic energy flow into a small volume, while the second term subtracts the work done by the field on free electrical currents, which thereby exits from electromagnetic energy as dissipation, heat, etc. In this definition, bound electrical currents are not included in this term, and instead contribute to S and U. For linear, non-dispersive, and isotropic for simplicity materials, the constitutive relations can be written as D equals E H equals 1 M B backslash display style backslash math D equals backslash verpsilon backslash math E backslash quad backslash math H equals backslash frac 1 backslash mu backslash math B B B B B B B B B E B B B B E B B B B B B B B B B B B B B B B B B B B B B B B where E is the permittivity of the material, M is the permeability of the material. Here E and M are scalar, real-valued constants independent of position, direction, and frequency. In principle, this limits Poynting's theorem in this form to fields in vacuum and non-dispersive linear materials. A generalization to dispersive materials is possible under certain circumstances at the cost of additional terms. One consequence of the Poynting formula is that for electromagnetic field to do work, both magnetic and electric fields must be present. The magnetic field alone and the electric field alone cannot do any work. Formulation in terms of microscopic fields. The microscopic differential version of Maxwell's equations admits only the fundamental fields E and B without a built-in model of material media. Only the vacuum permittivity and permeability are used, and there is no D or H when this model is used. The Poynting vector is defined as S equals 1 M 0 E X B backslash display style backslash math S equals backslash frac 1 backslash mu 0 backslash math E backslash times backslash math B B B B B B B B B B B B B B B B B B B B B B B B B B B B E E E E E E E E E E E E E where M0 is the vacuum permeability, E is the electric field vector, B is the magnetic field vector. This is actually the general expression of the Poynting vector. The corresponding form of Poynting's theorem is U T equals S J E backslash display style backslash frac backslash partial U backslash partial T equals backslash nabla backslash C dot backslash math S backslash math J backslash C dot backslash math E, where J is the total current density and the energy density U is given by U equals 1 2 E 0 E 2 plus 1 M 0 B 2 backslash display style U equals backslash frac 1 2 backslash left backslash verpsilon 0 backslash math E2 plus backslash frac 1 backslash mu 0 backslash math B2 backslash right backslash, where A0 is the vacuum permittivity, and the notation etwo is understood to mean the dot product of the real vector et with itself. It can be derived directly from Maxwell's equations in terms of total charge and current and the Lorentz force law only. The two alternative definitions of the Poynting vector are equal in vacuum or in non-magnetic materials, where B equals M0H. In all other cases, they differ in that S equals 1/M0, EXB and the corresponding U are purely radiative, since the dissipation term J, E covers the total current, while the EXH definition has contributions from bound currents which are then excluded from the dissipation term. Since only the microscopic fields E and B occur in the derivation of S equals 1/m0 exp and the energy density, assumptions about any material present are avoided. The Poynting vector and theorem and expression for energy density are universally valid in vacuum and all materials. Time averaged Poynting vector. The above form for the Poynting vector represents the instantaneous power flow due to instantaneous electric and magnetic fields. More commonly, problems in electromagnetics are solved in terms of sinusoidally varying fields at a specified frequency. The results can then be applied more generally, for instance, by representing incoherent radiation as a superposition of such waves at different frequencies and with fluctuating amplitudes. We would thus not be considering the instantaneous et and ht used above, but rather a complex vector amplitude for each which describes a coherent wave's phase, as well as amplitude using Faser notation. These complex amplitude vectors are not functions of time, as they are understood to refer to oscillations over all time. A Faser such as im is understood to signify a sinusoidally varying field, whose instantaneous amplitude et follows the real part of im jot, where O is the radian frequency of the sinusoidal wave being considered. In the time domain, it will be seen that the instantaneous power flow will be fluctuating at a frequency of 2O. But what is normally of interest is the average power flow, in which those fluctuations are not considered. In the math below, this is accomplished by integrating over a full cycle t equals 2p/O. The following quantity, still referred to as a Poynting vector, is expressed directly in terms of the Fasers as S m equals 1, 2, E m x h m asterisk display style math s mathem m equals t frac 1 2 math e mathem m times math h mathem m asterisk, where asterisk denotes the complex conjugate. The time averaged power flow according to the instantaneous Poynting vector averaged over a full cycle, for instance, is then given by the real part of Sm. The imaginary part is usually ignored, however it signifies reactive power, such as the interference due to a standing wave or the near field of an antenna. In a single electromagnetic plane wave rather than a standing wave, which can be described as two such waves traveling in opposite directions, E and H are exactly in phase, so Sm is simply a real number according to the above definition. The equivalence of Sm to the time average of the instantaneous Poynting vector S can be shown as follows. S t equals E t x h t equals re e m e j o t x re h m e j o t equals 1, 2, e m e j o t plus e m asterisk e j o t x 1, 2, h m e j o t plus h m asterisk e j o t equals 1, 4, e m x h m asterisk plus e m asterisk x h m plus e m x h m e 2 j o t plus e m asterisk x h m asterisk e 2 j o t equals 1, 2, re, e, m, x, h, m, asterisk, plus 1, 2, re, e, m, x, h, m, e, 2, j, o, t, backslash display style backslash begin aligned backslash math st and equals backslash math et backslash times backslash math ht backslash and equals backslash operator name re backslash left backslash math e backslash mathem mej backslash omega t backslash right backslash times backslash operator name re backslash left backslash math h backslash mathem mej backslash omega t backslash right backslash and equals backslash t frac 1 2 backslash left backslash math e backslash mathem mej backslash omega t plus backslash math e backslash mathem m asterisk ej backslash omega t backslash right backslash times backslash t frac 1 2 backslash left backslash math h backslash mathem mej backslash omega t plus backslash math h backslash mathem m asterisk ej backslash omega t backslash right backslash and equals backslash t frac 1 4 backslash left backslash math e backslash mathem m backslash times backslash math h backslash mathem m asterisk plus backslash math e backslash mathem m asterisk backslash times backslash math h backslash mathem m plus backslash math e backslash mathem m backslash times backslash math h backslash mathem m e2 backslash omega t plus backslash math e backslash mathem m asterisk backslash times backslash math left backslash math e backslash mathem m backslash times backslash math h backslash mathem m asterisk backslash right plus backslash t frac 1 2 backslash operator name re backslash left backslash math e backslash mathem m backslash times backslash math h backslash mathem me2 backslash omega t backslash right backslash and aligned. The average of the instantaneous Poynting vector s over time is given by s equals 1 t 0 t s t dt equals 1 t 0 t 1 2 re e m x h m asterisk plus 1 2 re e m x h m e 2 j o t dt backslash display style backslash langle backslash math s backslash wrangle equals backslash frac 1 t backslash int 0 t backslash math st backslash dt equals backslash frac 1 t backslash int 0 t backslash left backslash t frac 1 2 backslash operator name re backslash left backslash math e backslash mathem m backslash times backslash math h backslash mathem m asterisk backslash right plus backslash t frac 1 2 backslash operator name re backslash left backslash math e backslash mathem m backslash times backslash math h backslash mathem me2 backslash omega t backslash right. The second term is the double frequency component having an average value of 0, so we find s equals re 1 2 e m x h m asterisk equals re s m backslash display style backslash langle backslash math s backslash wrangle equals backslash operator name re backslash left backslash t frac 1 2 backslash math e backslash mathem m backslash times backslash math h backslash mathem m asterisk backslash right equals backslash operator name re backslash left backslash math s backslash mathem m backslash right. According to some conventions, the factor of 1/2 in the above definition may be left out. Multiplication by 1/2 is required to properly describe the power flow, since the magnitudes of m and hm refer to the peak fields of the oscillating quantities. If rather the fields are described in terms of their root mean square RMS values, which are each smaller by the factor 2/2 display style sqrt2/2, then the correct average power flow is obtained without multiplication by 1/2. Examples and applications. Coaxial cable. For example, the Poynting vector within the dielectric insulator of a coaxial cable is nearly parallel to the wire axis, assuming no fields outside the cable and a wavelength longer than the diameter of the cable, including DC. Electrical energy delivered to the load is flowing entirely through the dielectric between the conductors. Very little energy flows in the conductors themselves, since the electric field strength is nearly zero. The energy flowing in the conductors flows radially into the conductors and accounts for energy lost to resistive heating of the conductor. No energy flows outside the cable either, since there the magnetic fields of inner and outer conductors cancel to zero. Resistive dissipation. If a conductor has significant resistance, then, near the surface of that conductor, the Poynting vector would be tilted toward and impinge upon the conductor. Once the Poynting vector enters the conductor, it is bent to a direction that is almost perpendicular to the surface. This is a consequence of Snell's law and the very slow speed of light inside a conductor. The definition and computation of the speed of light in a conductor can be given. Inside the conductor, the Poynting vector represents energy flow from the electromagnetic field into the wire. For a derivation that starts with Snell's law, see rates page 454. Plane waves. In a propagating sinusoidal linearly polarized electromagnetic plane wave of a fixed frequency, the Poynting vector always points in the direction of propagation while oscillating in magnitude. The time-averaged magnitude of the Poynting vector is found as above to be S equals 1, 2, E, M, 2, display style langle s wrangle equals frac 1 2 eta e mathem m2, where m is the complex amplitude of the electric field and E is the characteristic impedance of the transmission medium, or just as 377 O for a plane wave in free space. This directly follows from the above expression for the average Poynting vector using Faser quantities, and the fact that in a plane wave the magnetic field Hm is equal to the electric field m divided by E, and thus exactly in phase. In optics, the time-averaged value of the radiated flux is technically known as the irradiance, more often simply referred to as the intensity. Radiation pressure. The density of the linear momentum of the electromagnetic field is S/C2, where S is the magnitude of the Poynting vector and C is the speed of light in free space. The radiation pressure exerted by an electromagnetic wave on the surface of a target is given by P rad equals S C display style P mathem rad equals frac langle s wrangle mathem C. Static fields. The consideration of the Poynting vector in static fields shows the relativistic nature of the Maxwell equations and allows a better understanding of the magnetic component of the Lorentz force QVXB. To illustrate, the accompanying picture is considered, which describes the Poynting vector in a cylindrical capacitor, which is located in an H field pointing into the page generated by a permanent magnet. Although there are only static electric and magnetic fields, the calculation of the Poynting vector produces a clockwise circular flow of electromagnetic energy, with no beginning or end. While the circulating energy flow may be counterintuitive, it is necessary to maintain conservation of angular momentum. Momentum density is proportional to energy flow density, so the circulating flow of energy contains an angular momentum. This is the cause of the magnetic component of the Lorentz force which occurs when the capacitor is discharged. During discharge, the angular momentum contained in the energy flow is depleted as it is transferred to the charges of the discharge current crossing the magnetic field. Adding the curl of a vector field. The Poynting vector occurs in Poynting's theorem only through its divergence, that is, it is only required that the surface integral of the Poynting vector around a closed surface describe the net flow of electromagnetic energy into or out of the enclosed volume. This means that adding a solenoidal vector field 1 with zero divergence to S will result in another field which satisfies this required property of a Poynting vector field according to Poynting's theorem. Since the divergence of any curl is zero, one can add the curl of any vector field to the Poynting vector, and the resulting vector field S will still satisfy Poynting's theorem. However, the theory of special relativity, in which energy and momentum are defined locally and invariantly via the stress-energy tensor, shows that the above given expression for the Poynting vector is unique.